Okay, so welcome to the Math Colloquium of Roosevelt University. This is the first talk for the fall 2023. And so Won Ahn from our department will talk about mass transport and interacting particle systems. Thank you very much, Won. I know that you are very busy these days, and thank you for being willing to give us a talk. So the floor is yours.
Thank you. So the introduction part and the background part will be might be somewhat difficult, but after the general definition and the patients and background, I'm gonna some specific examples that will be more interesting. Please bear with me. So here is a notations of first the graph. So the graph is consisted of it's called a G, and it is consisted of vertex V and the edges E. So you can think of vertex as this is the G2 graph, and these are the vertices, and the edges that connects the vertices, call it E there. And the E is the set of vertices, set of edges. Here V is the set of vertices. So for each of U, that N to the set of neighbors, U in G. So that means in this U, the neighbors are right here. There are four neighbors. The vertex U. And we call K as a Markov kernel on G. You can think of that as a transition probability from U to their neighbors. Here. There are certain probability that U to move to their neighbors. The sum of those probability has to be equal to 1. And if the the vertex is not in their neighbors, then there's no transition probability. So here is some more advanced notations. Let phi be some function or operator that goes from one vertex to another vertex, and we call this a group of phi, gamma k. Gamma k is the k preserving automorphism G. That means that even if you take the operate action on this vertex is U by this phi, the transition probability doesn't change. This kernel doesn't change. And in addition to that, also it's a three tuple, three component, the graph and the transition probability. This group of the operator acting on the vertices become a system. And also, we are not only considering this system, any system, we are considering the system with the following conditions. So this system has to have these following conditions. One is the transitive. Transitive means that this phi is this gamma k is a non-empty for any vertex U and V. So there exists some phi that phi of U is equal to V. And this unimodular, I'm not a computer science expert, so I don't exactly understand the definition of what the unipolar means, but it just tells you that if there is a phi such that phi of u is equal to u, and if you apply that phi to the another vertex, then group of those identity function or operator should give you the finite uh, set of the output. Okay, so your phi of v, and you have a group of identity operator on the u, put it on the another vertex v, it should give you only the finite number of output, vertex output, and it should be equal for any vertex, applying on the any vertex. And also it has to be infinitely accessible. That means that there exists some phi that if you apply phi multiple times, the vertex should be the set of vertex or set of the output vertex should be infinite. And also there should be some sequence of is a phi and phi to the n reaching to your original vertex. The probability of moving from here to here should be finite. Sorry, it should be greater than 0. So it should be non-zero.
Sorry, the unimodular property.
Uh-huh.
I am confused. The U is a set.
Yes, this is a I say this is a group, a set.
A set of the automorphism that sends you to you.
That's right.
What is the meaning of the bar? Is the
Bar is the cardinality or the number of so here like here's a p one of get the u p two and your so here this whole thing will be over one p.
But what is the I don't understand VUU times V. What is that product? It's very confusing to me.
Oh, this is just you're
The
applying
number of elements that are in that set times V.
no this is I should say that so here is a p VUU such that
Oh, I see. Okay.
so it's all set of this
V in that
VUU.
set you apply to V should be should be the same as all phi in VV applied to you.
That's right. Or apply to V.
Yeah, but in the other side, that should be equal to phi.
That's right.
Phi applied to you.
Yeah, this is another different V, right? This V is for
Yeah,
the VUU.
the phi that fix V.
Yes.
Right. Okay. Okay.
So yeah, the notation is kind of confusing, but
Yeah.
I will explain some examples. Might be give you some idea of.
Yeah. Okay. Okay.
So here is an example. This system which satisfies the transitive unimodularity and the accessibility. So this is the G2, and U is basically the x-axis, the value of x and the value of y. And also the transition corner, it's symmetric. So here, probably to in this direction or this direction or this direction, this direction will be the same. and 0 otherwise. So this is the simple symmetric random walk to the nearest neighbor. There's no jumps. And also we're gonna make a subgroup with this K preserving system as a set of a translation operator. So E of xy, you're adding that the value x, the x-axis, and value y on the y-axis. Then the transitive, under this system, this transitive, because for any v, if you put this value as a shifting jumping value, then G2. And also, it is unimodular because B 0, 0, so there is no shifting. It's the only operator we use for any. So this will be just V, this will be just E. So it's only. And also, it is infinitely accessible because if you think of the phi where you are just jumping to the right, so here's one, jumping to one right, no jump to the vertical axis. And if you do that n times, you're just keep going to the right, infinitely times. So there are like infinite set of vertices to the right from the U. So that give you the horizontal array. And also any horizon, any value on the horizontal array can be back to U by a positive probability. So this three components makes the system satisfying this the properties or conditions. And in general, actually, there are more systems that you can have the transitivity and the unimodulity and the accessibility. So the graph can be the Cayley graph. This is the Cayley graph, and or any GD, any GD graph, or any tree graph. This is a 3-dimension. This is the G3 actually. This is the T4. So every vertex have a 4 direction. Just call it a tree with a complete tree with a. Then and also the corner can be the same as the one that I explained in the previous slide, the transition probability to the nearest neighbor random. Finally, the gamma k, the operator is just a translation operator, the shifting operator that I show you the last slide. But there can be more. But this is the 3 examples that I can come with now. So suppose you have this system. Then here is the very important property that satisfies that system. Consider the gamma and k and the gamma k system with the transitivity, unimodularity, accessibility. Then the mass transport principle is satisfied. What is the mass transport principle? It's the so suppose G is the collection of random variable. We do this 2 vertices, and also B expectation of this random variable equal to the expectation of random variable after this E applied on the vertices. then for any fixed vertex, any fixed vertex on one side, and even if you switch the domain, the input, the vertices, the expectation of the sums are equal. And this property is applied in various correcting particle systems to solve very important problems. And the key is to define the random variable G carefully and creatively. So here is an example where the mass transport is applied. So this is called a parking problem. And let me introduce the initial setting first. An example of the, so initially, each vertex is assigned either by unparked car, a car that can be with a probability p, and a parking spot, 1 minus p. So each vertex is either occupied by the unparked car or the parking spot. When time starts, unparked cars simultaneously perform symmetric to the nearest neighbor according to the corner cable, transition cable. When the unparked car moves to the empty spot, that's the parking spot, then the car is parked. Each parking spot can only fit one car. So this means once the parking spot is filled, then other cars remain unparked even if it arrives at the parking spot. So here is some simulation done. It's a parking problem. So there are 2,000 vertices. This is in G. So there are 2,000 vertices, horizontal axis. And the red spots are, you can think of that as a parking spot. Okay. So, and the vertical line is the time, elapsed time. So when you go up there, then when you move up, that means that the time is elapsing. The red spot, parking spot, will not move. So it just stays. Okay? Stays the same spot. However, the blue one, the car will move around. And when it meets the parking spot, it's going to erase the parking spot and car. So they annihilate each other. When the probability of assigning car is 45%, then even after like many times passed, there are still many parking spots on the horizontal line. However, if you increase the probability of assigning car on the G, and you elapse the time, you can see that some of the parking spots are definitely moved, and because there are more cars driving on G, as time moves on, there will be less and less parking spots left. So this is the graph. Hopefully everyone understands the meaning of this graph. So here is actually the theorem developed by 2018 that if the P is again the probability that the unparked car is assigned, and let's say 0 is some initial vertex, some vertex V, then the probability that a car at 0 parks at some time when the 0 is initially has a car, is 1 minus 1 minus p over p. P is greater than 1/2. And the probability that spot at 0 is taken, given that 0 is the parking spot, is p over 1 minus p. P is less than 1/2. So here is the critical actually the critical probability, the 1/2, that if the p is greater than 1/2, then probability that the car is parking is less than 1. And if p is less than 1, then the probability that the parking spot is filled is less than 1. So before I showing the simple proof, here is some basic probability notation. That suppose and whenever I write I, some event A, this is the indicator function. So 1, event A occurs, 0 other. That means if you put expectation on this indicator function, there will be 1 times the probability of event plus 0 times the probability that event is not occurring is equal to probability that event A occurred. So expectation of the indicator function is same as the probability. So using that property and also using that the indicator function and also using this mass transfer principle, I'm gonna choose this g function g here with the two sides u and v as an indicator function that a car initially at u parks at v. So if you put that means if you put the expectation here, if you put the expectation g u and g 0 and u, that means a car at 0 parks at u. If you put the expectation 0 and so a car starting at 0 parks at u. And also that's equal to the sum of the probability that a car starting at u parks at 0. So then, because this is any vertices, so if you sum them up, and they are each probabilities are mutually exclusive, if you sum them up, the left side is the probability that a car initially at 0 parks. It's parking at somewhere, but it's gonna be parking somewhere. And equal to this sum is also mutually exclusive. It's any car in any vertices parks at 0. That means the probability parking spot 0 is parked in. So you have this equality there. So the next is I use this another condition of t. So this equality means that the probability that a car at 0 parks, given that a park at 0 initially, times the probability of car at 0 initially. That's the coming from the left side. Right hand side is another condition of t. 0 is parked in, given that 0 is a spot initially, times the probability that 0 is a spot initially. And we know that probability that the car is at 0 initially is p, and the probability that 0 is a spot initially is 1 minus p. You can replace this one by p, and this one by 1 minus p. And then the proof is completed by this following lemma. It's kind of very trivial, but actually the proof is not trivial. You have to use the couplings and to use stochastic dominance and things like that. And you can show that depending on where p is less than half or greater than 1/2, either this one is equal to 1 or this one is equal to 1. And you can find the explicit polynomial graph of the other side. So that's actually the very simple proof done in 2018. And so after that, there was a workshop, a stochastic spatial system. I was there 2019, and people working on these problems and also some derivation of these problems. Luckily, I was able to join their team. Some advice, or most of the time I just get help. I was able to. So I would like to give you some stuff that I learned from there, and also I would like to some recent result. So here, this time, we are slightly modifying this parking problem that the initial setting is identical to the parking problem. But there are some differences, or the initial setting here is that there's a probability p that car is assigned in a vertex, or 1 minus p. The parking spot is assigned, and also each spot can be occupied by only one car, and also car takes one passenger, also performs a symmetric to the nearest neighbor. But then here is some difference, that in the initial example, there was no interaction between cars. But this time, I would like to give some more condition on the interaction between cars, which is when the two cars meet, they coalesce into a single car. Or in other words, they collide, they get an accident, and one of the cars survives. Okay. And the passengers in two cars will be in that single car, because they need a ride. One of the cars should be yes, the carpooling. If the one of the car broke down, then the other car should help these other passengers. But suppose in reality, suppose if the sum of passengers in the two cars exceeds n, then we assume that the car doesn't collide. That's kind of not realistic, but that's why this is called n cap. We only take the passengers when the sum of those passengers are less than n. Otherwise, two car doesn't collide. Even if they collide, they don't merge into one. So in this setting, here is some computer simulation. And again, just like you saw in the initial graph, there's a horizontal line with the G. There are 2,000 vertices horizontally. And this is the elapsing time. So when you move up, the time is elapsing. And the red ones are, this time it's the colors are somewhat opposite. The red ones are the car, so they kind of put out symmetric random walk to the nearest neighbor. The blue one is the parking spot, so it just stays same spot. And if you increase the probability, then you see that some of the cars, they collide and merge onto just one. So the cars either disappear by collisions, or some cars meet this parking spot, they annihilate, they disappear. So there are two cases that the car disappears, either by collision with other cars or either meeting the empty parking spot. So how do we handle this situation with the mass transport property? Well, here is actually the theorem. This is actually the special case of the paper submitted this May, that suppose N is the fixed maximum passenger capacity car. That means they collide, the sum of those passengers are greater than N, right? Then we have this estimate, which is not explicitly calculated, but it's given. That's the expected passengers car parks. And also define this critical problem if the infimum gamma parameter, gamma over 1 plus gamma is less than, then here is the result. Probability that car at 0 parks, given that 0 is a car initially, is less than if it's greater than critical given by here, and equal to 1, so less than critical. If n is equal to 1, that means if there is no collisions, there's no correlation cars, then when the car parks, number of passengers should be always equal. And this result coincides with theorem 1 because this critical probability 1 over 1 plus 1, that's 1 half. And we are looking at the in 1 half. T greater than 1 half, that's going to be 1 half. And that means depending on if P is greater than P or less than P is greater than 1 half or less than 1 half, this probability changes. And also you can explicitly find the probability was 1 minus P over. Yeah, like that. And also note that the same probability, the critical probability with some algebra, just rewrite this as a form of gamma of P, then this infimum should be same as gamma of P less than P over 1 minus P. So how do we prove this? So this time we are using a different the random variable. So g of uv, but there's a subscript k here. So car starting at u parks at v with the k passengers. So there is extra constant or values k, and then we use this on this variable, we use the mass transfer principle. On the right hand side or left hand side, this side, it will be a probability that cars initially at 0 parks with the k passengers, given that 0 is there's a car at 0 actually, multiplied by probability that there is a car at 0. Actually, here should be some conditional should that car at, it's not a typo notation. It's not a typo. I couldn't write it. So out of size, slide size. And then we're solving over this each left side for k. So if you sum this one up to n, because the maximum capacity of the car is n, the passenger capacity is n, then it will be just a probability that p times the probability that car at 0 parks at somewhere. The right-hand side is more interesting. So recall that this GKUV, the car starting at U, parks at V, for K passengers. The right-hand side, so it will be 1 minus P times K times probability that a car, K passengers at car parks at 0. Why is that? Well, if K passengers, the car with the K passengers parks at this side 0, that means there should be at most K cars initially at somewhere in the vertices, K of them. They coalesce, then parks into 0. So each of them is the probability that K passengers car parks at 0, and there are K number of cars are coalescing, so you are multiplying by K. And also here is a given that spot 0, spot is 0. So, and then here is a multiply by spot, 0 is a spot initially. So that's why the K comes in here. And then summing over this K, so summing over this K, this one, the K times the probability of K passengers parking. So it will become an expectation, number of passengers the car parks. So it will be the 1 minus K minus P times this expectation. Then you have this by the mass transport principle, you have T equality for the left hand side and the right hand side. Then if you you can divide this by here. And then there is some lemma. This is it's very hard to prove actually. Honestly, I don't understand how they proved it. They wrote paper, but it's kind of confusing to me. However, I guess it works. That given P, that the probability that a car at 0 parks, given that 0 has a car initially, is less than 1, then if there's more cars, P prime greater than P, that means there are more cars initially assigned the graph, then still the probability that car at 0 parks, even that the 0 is a car initially, is less. And actually the proof is very kind of challenging, hard, but it requires the coupling and also the stochastic dominance, the survival time of the car. But yeah, survival time of the car. So if you have more cars, the vertices, we were able to prove that the survival time, the car before they getting parked, not coalescing but getting parked, is greater increase. There is some opportunity. So because of this, and also by the lemma 2, and also we have this, then the probability that a car at 0 parks, given that 0 has a car initially, is less than 1, any of P greater than is critical. So Actually, there are further results on this study. So let VT be the number of car visits to site 0 up to time t, the capital T. Then suppose the maximum capacity is finite. The capacity of the car is finite. Then the expected time, expected number of car visit up to time t is the probability greater than probability that the car doesn't park. This is correct because if p is greater than critical probability, then the probability that the car parks is less than 1, right? So this is true, then it's less than why this is greater than 0, is greater than 0, and divide by n times t. So this one tells you that as long as n is finite, the number of visits increases linearly by the time. And the proof actually requires another very interesting function g or mass transport principle. And the function g in that case is the indicator function that the car starting at u does not park in any site, any parking site. So this proof actually can be done by that another mass transport principle using a different random g. And here is another result that even if the capacity is infinite, can place the car can place infinite time, and the probability that the car doesn't park is greater than 0. These two conditions are met, then this time the expected value of the car visit is the probability that car doesn't park times the natural log of t. So number of visits is growing up by not linearly but natural log of t. In both cases, in fact, it means that the expected number of visits by car becomes infinite over time. So if you let t goes to infinite, so whether you have a finite number, infinite number, matter what is number in time is. So I'm moving on to last slides. I guess I'm in the finishing up faster than I thought. So the more general result has been, we actually studied and submit a paper on the more general result. Previous one was just a special case that type A particles, suppose type A particles and type B particles are assigned each vertices probability P and 1 minus P respectively. So this time, the type B, it's not parking spot anymore, but it's another particles in a supersymmetric random to the nearest. Each type of particle is a random nearest neighbor, but with a different jump rate. Jump rate means a different Poisson cloud. Poisson rate. So when particles of the same type meet, then they coalesce. And if the particle of different type then they annihilate each other. In other words, they got they disappears. Then that happens, then the results are very similar to the result from that parking problem, the police. However, there are some more additional result, but it requires more advanced math techniques. So I'll not discuss here, but the main tool that we used here is actually exactly same as the one that we used in the polishing parking problem. So that's pretty much it. Uh, yeah, if you have any questions, so ask.
Questions, comments?
I have a question.
Hello, yes.
Hi. Rowan is swinging in the background. I was curious about that result you said at the end, where if they annihilate, you get the same sort of result as the coalescing. So I can see how coalescing would make sense because, well, how coalescing like is going to decrease the number of cars on the board, but only up to a point. And then it seems like it would just, they'd be maxed out. But the annihilation seems like you could decrease it until, you know, one of the two types is completely gone. So like it feels like that would be different, but why is that similar?
Oh, actually, like
Any intuition? I'm just curious, big picture.
Actually, I didn't put here, but this one, the capacity will be infinite. This one will be finite, something like that. We're gonna do that. Then
okay, so it
the
eats all the finite stuff, and then the infinite one is just like full cars.
That's right.
Okay.
Well, this one actually
Just like
disappears faster.
Okay.
Because this one has an infinite capacity. So
Mhm.
when they call it, this one disappears faster than the one with the finite capacity.
Okay.
So it
Okay.
kind of give you some, I say some differences. There's a
Okay. Interesting. Okay. Okay. So the infinite capacity ones can always sort of shrink down because they're always coalescing.
yeah.
And if they were just by themselves, you'd get down to one. And then that
Mhm.
one squishes with a type A one, which have maybe, if they were by themselves, they get down to like a smaller number of like full cars.
That's right.
And then you're
that's
just left with some of the type A's.
Yeah, because there should be some point P, the probability of
Yeah.
assigning A, where here everything is full packed with the passengers,
Yeah.
while this one disappears. So
Okay.
yeah,
And are
thinking
all of
about
these,
parking.
yeah, are these all infinite graphs or do you have any on finite graphs or graphs that are,
So I'm not sure if can do maybe do in the I'm not sure if I can do this finite graph because I was thinking about
Mhm.
graph.
yeah.
So
I realize these are mathematically very different. I'm just kind of curious because that's, you know, one of them is like you're playing dodgeball and you're like knocking people out. And the other, you have the universe and maybe you have atoms and antimatter and seeing what happens, or I don't know. I'm just like thinking of what these models are and what they might mean.
Yeah. Oh, and what happens if both are finite or capacity finite or both are infinite? Is that something that has been studied too, or?
so I'm not sure if you can use the mass transport principle in the finite graph. If you don't use the mass transport principle, the finite graph can work maybe to the problem on the finite graph. But yeah, I don't know if there's any study on there. But infinite graph, you can use the mass transport and it's easy to solve problems.
Any other question or comment? Well, let's thank the speaker again. Thank you very much. Someone really nice and interesting area. And well, good luck.
Okay, thank you.
Okay. Okay. So I will stop recording. So